All right, today we're going to go on a little journey. We're going to uncover what really makes Python so powerful. And spoiler alert, it's not just the clean syntax or the giant libraries. Nope, the real story starts with its most fundamental piece, the humble function.
So let me just ask you right off the bat, what do you think Python's real superpower is? I mean, yeah, the clean syntax is great, and the libraries are absolutely massive, but that's just the surface stuff. Python's true magic? It's hiding in plain sight.
And it's this. It all comes down to how Python treats its most basic building block, the function. Seriously, this one simple idea is the key that unlocks pretty much every elegant and powerful feature in the entire language. And today, we're going to turn that key.
Okay, our journey starts with the absolute bedrock of Python's whole philosophy, this idea of the first-class function. Just about everything else we're going to see today is built right on top of this one powerful concept. You see, in Python, functions are what we call first-class objects. Now, think of it this way. In a lot of other languages, functions are kind of special, locked away things. But in Python, a function is just like any other piece of data. You know, like a number or a string. You can stick it in a variable. You can pass it to another function, like a little gift. Or you can even have a function hand one back to you as a result.
So what does first class actually mean in practice? Well, it means you can assign a function to a variable, just like you would with the number 5. It means you can feed one function into another one, like parts on an assembly line. And maybe the wildest part, you can have a function literally create and return a brand new function as its output. This flexibility is the engine for everything that's about to follow.
And because functions get this first-class VIP treatment, they can become incredibly flexible, especially when it comes to the information we give them, what we call their arguments. This is where Python gives us these two amazing tools, args and quarks. Just think of them as universal collectors. Args is like a magic bag that scoops up any extra unnamed arguments you throw at a function and bundles them into a neat tuple. And quarks, it does the exact same thing, but for named arguments, organizing them into a handy dictionary. This lets us write single functions that can handle almost any input you can imagine, making them just wonderfully adaptable. Now, what if you need a function for just a tiny one-off task? You know, you don't want to go through the whole ceremony of death, giving it a name, all that stuff. Well, that's exactly what Lambda functions are for. They are these small, anonymous, unnamed functions. They trade a little bit of power for a ton of convenience. You're limited to a single expression, but you can write them right there, on the spot, exactly where you need them.
So when do you actually pull out a Lambda? They're absolutely perfect for these quick throwaway operations. You'll see them all the time used as arguments inside other functions like map or sorted. You know, places where you just need to define a simple rule on the fly without all the fuss. It's the ultimate tool for functional brevity.
Okay, so far our functions are flexible, but now they're about to get smart. This is where the function develops a really cool new ability, a memory. Let's talk about the power of closures. So a closure is a function that actually remembers the environment where it was born. Think of it like this. It's a function that carries around a little backpack of variables from its home. And even after its parent function is long gone, finished its job, that closure still has access to everything in that backpack.
So how does this magic actually work? Okay, first, you have an outer function that creates a variable and then defines another, nested function right inside of itself. Step 2, that inner function reaches out and uses the variable from its parent. Then, and this is the absolute key, the outer function returns the inner function itself, but it doesn't run it. And that function that gets returned? It now has this persistent state, this memory of the variable from its birthplace. It's like a mini object, but without ever needing to write a class.
All right, we've seen functions become flexible, and we've given them a memory with closures. Now we get to combine those ideas to unlock a true Python superpower, the decorator. This is where functions learn how to modify other functions on the fly.
So let me paint a picture for you. It's a classic programming problem. You've got a function. It works perfectly. But now you need to add something to it. Maybe some logging, or you want to time how long it takes to run. How do you do that without ripping apart the original function and potentially breaking everything?
The elegant answer is the decorator. A decorator is a function that takes another function as its input, wraps it up in some new logic, and then hands back the newly enhanced version. And how does it work under the hood? Well, get this. It's a perfect real-world application of the closures we just learned about.
And you see decorators everywhere in modern Python.
They're used for logging when a function gets called, timing its execution speed, or, and this is a big one, in web frameworks like Flask or Django for checking if a user is logged in before they can see a page. They let you add incredible power without cluttering up your original code.
Let's just break this pattern down real quick. First, you've got your original function. That's your core logic. Then you have the decorator function, which is the wrapper that accepts your original function. Inside that wrapper, you write your new logic, what happens before or after the original function runs. And the final result? The decorated function, which is your original logic plus all that new behavior, bundled up as one.
Okay, decorators are amazing for adding behavior to existing functions. But what happens when your needs get more complex? What if you need to bundle related data and a whole bunch of functions together into a single, organized, reusable unit?
And this is where our functions journey leads us to its bigger, more structured cousin, the class. When you really need to bundle data and behavior together for the long haul, you need a blueprint. You need a class.
So, what is a class? It's a blueprint. It's a template that defines a set of attributes, that's your data, and a set of methods, which are really just functions that belong to the class. It is the go-to tool for organization and reusability when you start managing real complexity.
The core ideas here are pretty straightforward. You've got the class, that's the blueprint, then you have an object, which is a specific thing you build from that blueprint. The __init method is just a special function that runs automatically when you create a new object to set up its initial state. And self? Don't let it scare you. It's just a way for the object to refer to itself.
And this brings our entire story full circle. On one hand, you have decorators. That's the functional way to add new behavior to existing functions. On the other hand, you have inheritance. That's the object-oriented way. It lets you create a whole new type of object that gets all the features of a parent class and then adds its own unique twists. They're two different tools for two different kinds of problems.
So there you have it, from a simple recipe, a first-class function, all the way to an entire blueprint for an object. The incredible power and elegance of Python really truly begins with that one fundamental idea, treating the humble function with respect as a first-class citizen. So now that you've seen the whole journey, from a simple function to a stateful closure to a powerful decorator all the way to a class, I've got a question for you. The next time you sit down to solve a problem, which tool will you reach for first?